All right, a little bit about Morocco. Fez, with the oldest continuously running university, Karain University. Nelson Mandela had a profound effect over many, many people. When we were growing up, South Africa was going to be the country that had apartheid in this modern day and time. And his words are that education is the most powerful weapon which you can use to change the world. I'll leave it at that. We'll continue our discussion. We have talked about nanotechnology, how we, what are the technology drivers, what are the, and we looked at some examples also. So just to recap, because to put in perspective, living things, red blood cell, for example, is about 10 micrometer. And that's the size where we start talking about microelectronics. So left-hand side, you see in the almost in the middle is the biological thing, and the right side are the man-made things. When you get into the regime of few micrometers, that is where bacteria fall. And that's where it is written, it's called MEMS. We call this MEMS. We'll talk about MEMS today. Because if we understand MEMS and we understand how we create MEMS, then the next logical step is to create smaller things, which is nanoscale or nanotechnology, or there are many different ways how we approach it. We call it NEMS, we call it nanofabrication. But the idea is that below 100 nanometer, when we make something, we call it to be part of nanotechnology. So going forward, how do we define bio-nanotechnology? So now it is a broad field. The idea is that it has many different directions. It is micro and nano fabrications, micro and nano electromechanical systems. But when we make those systems, we do this bio and chemical measurements, which can go from cellular to subcellular. And when you go subcellular, we get into molecular levels. So if I were to make a drawing, I would go from making things smaller, then looking at the chemistry or the living things on the other side, and we come from both sides. And we use technology, we use new techniques, but the idea is how do we interface those two things? Why it is a big issue? Because if you think about it, engineering is about cold, hard machines, right? Metallic, hard surfaces, solid surfaces. But when you think about living things, they are not cold, hard, solid. They are mostly in liquids, right? And they are composed of lots of chemicals. So these are two areas, two different approaches that are coming together. How we enable it, we work on different new materials. We work on making interfaces, new interfaces from those existing materials so we can measure living systems or measure things or characterize things that are there in the living system. Or you can say we want to characterize the activities that are happening in living systems. And it's not different than any other kind of sensor. You think about temperature sensor. So what does temperature sensor do? It is measuring an environmental phenomena, which is temperature. If you think about a pH sensor, that's again a hard device, but what it is measuring is the amount of radicals, hydroxyl ions or hydrogen ions, which tells us what is the pH. Is it acidic or basic? If you think about it, it's no different than that. That we want to make things smaller and we want to characterize functions or activities that are happening at small scale. Now, we want to first characterize, so we have some baseline measurements, and then we can set systems that can look for changes in those systems. So if you think about the systems or the man-made side, we talk about microfabrication. Or we talk about, we had big sensors, but now we want to make them smaller. We want to, the word is miniaturize. We want to make them smaller. And that trying to make things smaller has been pushed a lot more in silicon. Silicon, because that's the device industry, that's the transistor industry, that's what you call microprocessor industry, or that's the RAM industry, right? So all the things that go into computation, and that became multi-billion-dollar industry. Now, in that industry, there is a process called lithography, and lithography has been the cornerstone, or the most important process in silicon industry. But we will touch upon silicon, but we will go as much into silicon, which is necessary for us to understand microfabrication and then nanofabrication. Because now we have gone from silicon to many other materials. We have gone on to many other methods, non-silicon methods, or non-silicon materials for that matter. And in those materials and in those methods, we are not depending exactly on the methods that are used in on device industries, because now we are writing things directly. We are using biological molecules. We are basically somewhere in the middle, where you come from top down, we make something, and we come from bottom up, where we play with the chemical nature of things. So hence we have developed many non-traditional techniques, and they are now being applied to miniaturize things and to make things smaller. But this has not happened in one day. So there is a history behind. This is a small picture. I know it's hard to read. We'll focus on some parts of it later on. But right now, I just wanted to share that microelectronics, which is device industry, MEMS, nanotechnology, and biotechnology, over years, they have grown. They have seen new approaches, new equipment. They've seen new kind of materials. There have been many new discoveries. People have got Nobel Prizes along the way in all four domains. But where we are now is we would like to see and we'd like to understand. So that will help us define the path forward. So we'll come back to this picture later on, but right now I just wanted to focus on MEMS. We have talked about microelectronics. We'll talk more about microelectronics as we go forward. But let's focus on MEMS. MEMS is a short acronym for micro electromechanical systems. Now, if I break down these first three words, micro relates to size, electro. We have many electrical engineers. How would you define an electrical system? What is an electrical system? What
Uh,
is
so the system is related to decrease the power or consider on power systems,
power?
voltages,
Yes,
or
right, right. Exactly. So it's related to charge, right? So it's related to electrons or holes if you go into semiconductor devices. So the basic idea is we are talking about voltage, potential, and flow of current. That's an electrical system. When you say mechanical, what comes to your mind? What is the fundamental mechanical device? Give me
cell
just
structure.
structure. Is that mechanical? Can somebody give me an example of a mechanical device? A simple, most fundamental mechanical device.
A motor?
A motor, right? A motor is a most fundamental mechanical device. What does a motor do? Converts electrical signal into motion, right? Converts an electrical signal into motion. When you say motion, something that moves. So MEM systems are systems which have moving parts. That's how you can understand. But they are very small. If you're thinking about a motor, say we have a motor like 1 foot by 1 foot motor that we use for, I don't know, pumping water. And then you talk about motor in a toy, right? Which may be a centimeter by a centimeter. And now we are going into microscale motors. So hence, a micro motor would be an example of MEMS device because you have to actuate that motor by providing it current. So this happened across over years. So they started from radar, where they were talking about semiconductors. But then the big change or big thing came when in 1979, it says here, the first micro machine accelerometer is developed at Stanford. Do you see that on 1979? So that's, if you think about it, that's the first major demonstration of a moving thing at micro scale. And then there's, we got scanning tunneling microscope where we are moving things or scratching things on a surface and we are looking at the tunneling current change and that translates into an image. We'll talk about that later on. But 1984, polysilicon, now there are some keywords here which we will repeat and my goal is that we understand what do these keywords mean. So here it says, there's this word, a bunch of words, surface micro machining process, right? So it's developed at Berkeley and MEMS and ICs can be fabricated together for the first time. 1984. This is what do you call the turning point in the history of MEMS. Micro machining, we do machining, right? Like you have lathe machine where they can put some metal piece and they can move material, they can cut material, they can file material. When you say micro machining, we are removing material, adding material, depositing material, etching material at micro scale. That was a major step forward. Why? Because we can think of doing machining and making parts at large scale, but making them at small scale, at micro scale was a major step. Why? Because we didn't have tools to do things at that small scale, right? So if you know machining, we have lathe machine and then we have big tools that we hold in hand, right? I don't know what they call, Randa, Cheni, this used to be the word, right? Which are machining tools. But now at micro scale, you need smaller tools. So that changed. 1985, buckyball. That's a nanomaterial. We'll talk about that when we talk about nanomaterials. But these steps show us, and then 2000s, we got to a point where MEMS devices were everywhere. Can somebody give an example of a MEMS device they use every day? Ahmed, you're sleeping. Ahmed Naeem, you're on your bed, you're on your pillow. We cannot hear you. It seems you have a headache. Are you fasting today? It's okay, I'm just kidding. Ignore me. Now, all right. Give me an example of a MEMS device we all carry around.
Mobile phone,
Do you have
sir?
a moving... Say it again, Habil.
Mobile phone, sir?
Mobile. Do you have a
Mobile
moving
phone?
part? Okay. Do you have a moving part in your mobile?
I don't say, but the moving part is, I think, we guys are the moving part. We carry it around.
The answer is yes. The moving part is somewhere packaged inside your cell phone. It's accelerometer. The most fundamental device is accelerometer, right? That's how when you change the orientation of your phone from straight to sideways, your YouTube movie changes orientation, right? So that's a very fundamental device, which is, it's very common. You'll be amazed when we see today that MEMS devices are everywhere. MEMS devices are making our life working today. So there are actuators, sensors, mechanical structures. They are built into substrate. And where do we find them? We find them in phones, tablets, cameras, gaming devices, cars, lights. Look around, these LED systems which can, you bang them and they change color. They all have MEMS systems in there, MEMS somewhere. And this is an example of a motor. There is exact same principle that we know for a motor as at large scale. I know if they teach you BL Thraja or not. These motors, they had synchronous motor, asynchronous motor, and I don't know, the different winding motors. It's no different than that, but it's at micro scale. This is an SEM picture of a MEMS motor. So we got inspiration. We still get inspiration from many places. Living systems. These are SEM images of a fly, eye of a fly, and a red blood cell, right? So size scale, we have to know 8 micrometer for red blood cell, and then fruit fly eye is composed of many, many, many smaller micro scale things. And when we come into man-made, this is a real picture of an accelerometer. Now, when we look at these pictures, and we'll be looking at many of such images and pictures, what we see, the first thing which we want to see is we look at the scale bar, like here it is given. What is the size here? 10 micrometer. So that size is for us to know, and we take that dimension and we can take it across other parts of the images, and we can find out what is the dimension of other places. So if there was a way for me to select this and take this, oh, this is going back. Taking the whole thing, I can put it somewhere next to it. You see, I measured that 10 micrometer. Now I can move it around. This is 10 micrometer. It's far away, but in the image, it's slightly smaller than 10 micrometer. It's showing as 8 micrometer, right? So I can rotate this also. Maybe I cannot on this one, but when we have figure, we take a ruler, we can always estimate what are the sizes of other parts. Now, there are some parts here which have written as movable plate. Some parts have been written as fixed plate. So accelerometer is nothing but interdigitated electrodes, and one side is fixed, the other side is moving. And we are measuring, there are many ways how we measure. We generally, if we can measure capacitance, if this goes up and down, the capacitance will change. And that's how we measure how much acceleration is faced or felt by that accelerometer. That's a 2D picture of accelerometer, right? So one side is fixed, the other side is on a membrane, movable membrane. How fast you accelerate your car or your phone, or you're running, or you have your GPS on, that's going to measure how fast you are going. Now, this is the moving part. And there is electrical part to it, hence the MEMS, right? So we have embedded transistors, embedded resistances, capacitors, and the whole 9 yard as you would have on a breadboard. Now that circuit is going to get the whatever capacitance change or resistance change is there, and gonna give out a number which will tell us how much is it doing, right? And these are cheap, like dirt cheap. This is a fairly decent accelerometer module, which is for $15. Yeah, you can buy it on Amazon or any website for $15. And this has extremely low noise and extremely low power consumption, right? So you can make a circuit that drives, we can make a driver circuit to give appropriate voltage and measure the signal. You can see on the chip, it says it has 6 connections, ground, UCC, X, Y, Z. So it can give you 3 direction signal, up, 1, X, Y, or up, all 3 direction, 3 dimension, right? It's an example of a MEMS device. Now, when we design MEMS, there are different ways how we do that. We can take a big system and we can try to scale it down. But we know from after reading Feynman's paper, we know that it is not always possible to scale down a large system, right? You know this by now. And we can discuss why it is not possible. The simple reason is the you can scale down the dimensions, but you cannot scale down current density. You cannot scale down, if it's a moving thing, then you cannot scale down the resistance, the friction it may feel. You may not be able to scale down the effect of one device on the other device, what you call stray capacitance, right? Electromagnetic interference, EMI. So it's not always possible to scale things down. But if we have to undertake electromagnetic properties to make sure we don't interfere with each other. Now, why we scale down in some places? Some places we want to scale down so we can have many more sensors. So our sensitivity goes up. Or we want to have redundancy, which means we want to have more than one sensing element. So if one goes bad, the other can measure. Or we want to have it in a way like this micromirror array chip is. So micromirror. Why would we use micromirror? Can somebody guess? Where would you need micromirror array? All right. There are two things that would happen here. One thing is you can adjust the reflection, you can adjust the orientation of the mirror. So you can make, if it's like this and it's reflecting, you can make it like this, it will not be reflecting, right? Number one. Number two, you can polarize the mirror, which means you can reflect some color and you can stop some color from going back. Where do you think we would have such application of such a thing? Projection. We all have projectors in classrooms, right? Projection. Movies. Have you seen movies? They use projectors to throw light on the screen, right? We want to use them to have sensors. Hamza says sensors. Yes, sir. Now, the way we have CCTV cameras, right? We have motion detecting CCTV cameras. They don't stay on, they turn on only when they feel some movement, right? So there is a value to detecting or reflecting light. But the huge industry with these is night vision or light projection, right? Night vision, soldiers, light projection, entertainment. So if you look at this one element of this micromirror array, the center part is reflection, and then we have the multi-turn frame where we can either increase the reflection or reduce the reflection, right? And so much so, they have this upper thing is a light projector to watch movies or to give presentations. You can put it in your pocket. It's so small. And it's just $90. It's not too expensive. How much is $90? 150,000 rupees? Right? 1.5 lakh. You are carrying a projector in your pocket. How have we reached there? Because we can miniaturize. We are using MEMS. Now, it's not just that. There is medical applications, blood pressure, glucose sensors, cameras that we can digest. Why would somebody want to digest a camera? Do you know why would somebody want to digest a camera?
Medical tests.
Medical. What would? Yes. Medical. To do what?
To do tests, I guess.
What kind of tests?
I think like take a look inside. I think there's one where you look at your digestive system.
Endoscopy, sir.
Endoscopy, right? Digestive tract, polyps. There's so many things that they have to, right now, they have to use in very intensive procedures which are not comfortable, painful. A patient has to wait before and after to prepare. Exactly, Hamza. It's more than that. Disease, heart, blood vessel. Yes, now we are talking. So we can just have a MEMS camera and send it in. We can have a MEMS RF antenna. There's no RF MEMS, it's an area in itself. RF, right? People work on RF. It's not RF, it's RF, radio frequency. RFID tags. Now, when you have a warehouse, you have millions of items to drop ship on Amazon. We cannot possibly count all of them all the time, but we can put RF tags on them, and you can walk your sensor and it's gonna scan all of those just by walking next to them. These are MEMS devices. Printers. Now the days of desk jet are almost gone because laser printer is much cheaper now. But that has been one area where we had, if you had ever chance to take a look at that inkjet desk jet cartridge, it has micro scale holes in it through which the ink comes out. Accelerometers, image stabilization. We all know that, right? We like take selfie and it's moving, shaking. That's where these things come. They did put these on uh, contact lenses as well to measure liquid around our eyes, which can have molecules or levels of things that can help with glucose sensing. There's been, for sure, I have been on some panels where they were looking for some cancer-related molecules also in the tears. It was related to some specific cancers, but that's also a place where MEMS kind of things can go into human eye, and they can keep on measuring things as we go. So we know chain on a bicycle, right? That is another thing that has been implemented, and it's a common thing, micro chain drive. So where does it take us? Where do we go with MEMS? Robots, robotics, medicine. We talked about few applications, not just a pill that you can take, a thing that we can inject, right? That can look for arteries. That you have to know that eating mechanism is different than blood mechanism, right? They're different systems. The pipes don't run into each other. They have different piping. Food has different piping, right? So in a similar way, they can be systems or organs where we want to very specifically in that organ want to see what's going on. They can be, now when we say IoT, IoT is a separate topic, but the idea is there are newer communication technologies with which we can spread sensors and they can talk to each other. We can swarm a region, or we can, maybe it's a field where we want to grow some vegetables, farming, where we can put these MEMS devices, sensors, or to either measure something or to actuate something. Right? Now, this is a basic fundamental introduction to MEMS. We want to go from here to BioMEMS. And BioMEMS is then simply stated application of MEMS systems to either measure something which is biorelated, is either to process something in a biological system, maybe to deliver a drug or a sensor in a living system, maybe analyze something in a living system, maybe construct something related to biosystems or chemical systems. So they all come under the umbrella of BioMEMS. We'll talk about that next time, right?